Hello and welcome to What to Expect from Art of Math by Michael Zhang. The first thing you need to learn is what phi is. Phi is 1 plus or minus the square root of 5 divided by 2, and depending on if you add or subtract, you can get the small phi or the big phi, 1.618 approximately or 0.618. Now I'm going to show you how to draw the golden section. Start off with any length of line and draw a line half its length, 90 degrees to it, perpendicular. And then from your half, you find your D and then you find your G, indicated by the star. Now how does this work? Well, we'll prove it with Pythagoras. One side is 1 and the other side is half. And the hypotenuse, therefore, is plus or minus the square root of 5 divided by 2. Now CD is equivalent to half, and if you add it with the square root of 5 divided by 2, you get phi. 1 plus or minus the square root of 5 divided by 2. Now here is an overview of the calculations. Now I'm going to draw the golden rectangle. You start off with a square, and you find the midpoint of one of the sides. Then from using your compass, connect this midpoint to one of the vertices of the square and then draw down. Now you have the golden section, which you just extend to get your golden rectangle. And the golden rectangle displays cell similarity, so you can easily create smaller rectangles of the same ratio within it. And you can use these rectangles to create the golden spiral, as seen here. Now this is the golden spiral. It contains phi. Now I'm going to redo everything I did so far except on Geometry Sketchpad. You will notice that Geometry Sketchpad has such features as construct and calculate, which make sketches a lot easier than doing them by hand, especially with this circle tool, which replaces the compass quite easily. You can even features an enlarge tool to make your shapes bigger. Now I'm going to recreate the golden spiral, except on Geometry Sketchpad. With the calculate feature, I noticed that the ratio of the smaller rectangle inside the original rectangle is the same, meaning that this method works. Now this is the golden spiral. So what is this golden spiral found in? Well, it's found in nature in the form of the conch shell. And it's also found in architecture in the form of the spiral staircase found in an opera house. Now this is an example of regular tiling using a hexagon and only a hexagon. Now this is an example of semi-regular tiling, since it uses more than one regular polygon to tile the plane with triangles and 12-sided polygons. Now this is irregular tiling, since I'm not using regular polygons. And you can alter these irregular polygons to create very strange shapes, such as this dinosaur head. And it tiles the plane quite easily. And this is a shark I did much earlier. And I transferred this design onto tracing paper. And with lino tool and scalpel, I carved away at some plastic elephant skin to create a plate for printmaking. And with this registration made of plastic and paper to protect the table, and also this newsprint to protect the table also, and this brayer, or paint roller if you prefer, and some ink, and I stress ink and not paint. I rolled it up on this palette and applied it to the plate, and applied some washi paper and rolled it up, and this is the finished product. Now with enough of these prints, you can create a pyramid with them, as seen here. Now origami is an art that neither subtracts or adds, just simply a piece of paper and fold with infinite possibilities. You can create fractals, as seen here with this folded curved fractal. Now here's a very simple fractal, starting off with Pascal's triangle. Follow this rule. The next cell is always the sum of the two cells above it, and treat all empty cells as zeros. and just fill down, making Pascal's triangle. Now, when you filled enough of this triangle, fill out all the odd numbers, and you get Sierpinski's triangle, which shows cell similarity, like all fractals do. And as you notice, this fractal sort of resembles the Triforce from the Legend of Zelda series, if you play that. Fractals are found everywhere, in paper, and also in nature, in the form of these tree branches, as each branch branches off to more branches. With the iterate function of Geometr's Sketchpad, it is quite easy to create fractals. For example, the Sierpinski triangle, and also the Sierpinski carpet, by starting off with a square and dilating it 1/3 of its original size, and splitting the square into 9 parts. So what are the applications for fractals? Well, they contain infinite surface area in limited amount of space. It can be used in cell phone antennas, like this. Now, here are the credits. This video was made by Michael Zhang, and thanks to all who helped me manipulate the camera, which I couldn't since my hands were quite full at the time. Now here's the image bibliography. Thanks to these websites I got these pictures.